We're going to get started here. You came to the Edge and IoT Working Group deep dive. We had another session yesterday that was very well attended. I see a lot of you familiar faces, so I think some of you carried over. But if you didn't, I'm going to go into a little intro very rapidly, probably not covering or explaining those slides, and I'd encourage you to go look at the recording. That said, we've got 4 presenters here from the Edge and IoT. Why don't you guys stand up and turn around, and they'll take the stage in a moment, and I'll get started. So the agenda is we'll have an intro, we'll cover Edge workloads, some challenges that you would typically incur with these workloads today, and at the end Q&A. If it's anything like the intro session, we're going to have a lot of interest in Q&A. We'll probably move it out into the hallway so that we don't, we're polite to the next speaker here. So they've bookended these talks with very little gap in between. Oops. So some use case examples here. Well, you can read the word cloud faster than I'd read it to you, so I'll say no more other than look at it now and I'll move on. One of the things we covered yesterday is that Kubernetes has a lot of similarities to what people are trying to accomplish in the edge space, in that it's a control plane made for controlling more or less IT workloads in a commercial data center. It featured a standardized API with tools, and it instigated a very rich tool chain of collateral things for metrics monitoring that could potentially be valuable in the IoT space. But the IoT space is a little different in that many of these are resource constrained. They're not close to infinitely expandable like the view you might think you have in a public cloud. They potentially have very special networking requirements, which we'll cover later on in the presentation. And they have challenges of unattended and disconnected operation. Another thing that's different, you've got potentially many more of these very small things than you'd have in a traditional IT data center setting. That said, I'll bring up Preston Holmes from Google, and I'll let you introduce yourself.
So really quickly, the way we're looking at this is exploring how Kubernetes sort of intersects all of these aspects of the edge. And what we've recognized is you can somewhat partition into these 3 boxes, and we'll cover each of them in a section that is workloads that you want to run on the edge that simply run on top of Kubernetes, challenges that can be addressed by features or capabilities built into the Kubernetes system itself, and then things that you need to solve for that aren't addressed directly by Kubernetes explicitly. So Dejan's going to cover first the section of things that people tend to want to run on top of Kubernetes.
Yeah. So the first question people ask about why would you run anything in the edge, and that's the first thing we try to identify is like what kind of workloads you want to move closer to the edge and reap some of the benefits. And in the next couple of slides I will try to walk you through that and try to address some of the existing functions and features of Kubernetes that are tied to a specific type of workloads that can be covered with that. So first of all, it's the workloads related to data ingestion and preprocessing. So basically, coming from the IoT use cases, you have a lot of devices producing data. So how you onboard these devices to the cloud, and how do you gather this information from the different kind of sensors using different kind of protocols, and how you basically kind of normalize the data you're reading from different kind of devices. So first level here is what we sometimes see is that dealing with this protocol conversion on the network level. So basically, a lot of constrained devices are not even TCP based. So we need to have some kind of workloads that will use near field protocols to get data from the wire and actually onboard this device to IP-enabled world. So getting them to some kind of usually some kind of standardized messaging protocols like MQTT or AMQP or HTTP to being able to be processed and sent further on to the cloud. But even if you get that data in a consumable way by the cloud, you usually want to do some kind of structuring of the data, giving it some kind of semantics and some kind of meanings. So these kind of workloads are there to basically try to convert all those different kind of protocols, different kind of meanings in some kind of meaningful way for a particular IoT edge solution. So that's where different kind of open source projects like Worto and standards like LWM2M come into play, trying to make sense of the readings and of the data we are collecting on the edge. On the other side, we'll talk a bit more about the challenges, but usually you don't want maybe to send all the data back to the cloud, so you want to do some kind of pre-processing there. So basically trying to do some kind of a streaming, for example. You don't want to send a temperature reading every couple of seconds. You want to send an event when the temperature actually changed. So these kind of workloads are also belong closer to the edge, trying to filter vast amount of data and create meaningful events that are actually useful for the cloud applications. So that's something also that people usually want to move closer to the edge. And finally, you want to tag some of these data, add a proper metadata there. So maybe add some more information that are not provided by the underlying hardware. So putting things like location where the data was generated or identity of some kind, and put some security tokens there, just that the sources of the data can be properly recognized there. So we are talking about all these these things, and you can see in the box downstairs. So these workloads belong closer to the edge. They don't belong on the cloud. And basically, what you're saying here, there's nothing special about this. So people are doing these kind of things in IoT gateways today, or different kind of solutions. So this is just a generic workloads that needs to be containerized, and what we want to provide is for ways for people to being able to use Kubernetes control plane to actually deploy these kind of workloads on a specific nodes that will run on the edge. The other thing is that in many environments, for example, having industrial IoT environments or some remote like oil pipes and things like that, the bandwidth can be usually a big problem. And what people want to do in those kind of use cases is to have like a reliability of their workloads and possibility to run them even when the network is down and the network is very limited. So for that purpose, usually there are two solutions coming to play, and those are moving the workloads based dedicated to buffering data on the edge and caching it locally come into play. So people tend to put message brokers closer to the edge, and they try to put like databases of all kinds on the edge nodes, so that other workloads running there can have that impression that they're always connected to the cloud, even if the reality does not reflect that. And again, this is nothing new, and only concern when you want to run something like this inside of the Kubernetes and other system is that you can always need to have in mind that these kind of solutions are solutions for a temporary offloading of data or temporary buffering of data, because usually resources on the edge is problematic, and storage, for example, is one of those resources. So you would be able to do this kind of buffering and caching for a little while, and then you would need to have strategies to deal with the situations when you reach those limits. Next type of the workloads that are usually and are very popular is latency, and that is how we're gonna provide applications that can basically provide a quicker return of the results to the end users. And for example, thinking about the game servers and things like that, where every milliseconds changes the dynamics of the game. So having kind of the workloads running closer to the online gamers makes a big difference. And we see a lot of interest in these kind of things being one of the drivers for the edge computing. So one of the things that we identified is that like serverless and functions are a good fit for this kind of the world, and what we will try to do in the future is to evaluate how we can collaborate and reuse some of the efforts within the CNCF community today, like cloud events and Knative, to try to see how to use functions and bring them closer to the end user by deploying them on the edge nodes, and thus reducing latency for the end users. But also the other two things that are related is compute offload. So in the same sense, you might want to do some heavy processing, like renderings and things like that on a hardware that sits closer to the end users. And finally, the final use case could be AI and machine learning, where we can see two kind of things. Is that you would deploy train models on the edge, or basically use edge to train specific models specific to the environment where the node is running. And today we have a couple of features here, and we also saw some of the demos on this topic also, where you can use stains and tolerances of the edge nodes to be able to provide a particular workload to an appropriate node. So the node that have appropriate GPU hardware, GPU resources, and things like that. So with this, I would wrap up about like why would you like to run something on the edge, and some brief descriptions of what's available today in Kubernetes to do that. So I will hand over to Preston again to talk about some of the challenges that can be solved.
Thank you. So I'm going to talk about just a couple features of something that's already available and built into Kubernetes that I think ends up being more important often in an edge environment. And this isn't meant to be comprehensive. I just sort of picked a few things to dive a bit deeper into, since this is a deep dive. And the two I'm going to talk about are related to prioritization and network. So I'll sort of set up why these are relevant in an edge environment. So edge environments are more likely to be incapable of scaling out. If you have a Kubernetes cluster on the cloud and that cluster becomes sort of overloaded, you can somehow often find a way to provision more nodes and add them to the edge, or add them to the cluster. Whereas in the edge environments, you're pretty much often you have what you deploy at the beginning, and there's no real way to add additional compute. And when that is the case, prioritization becomes more important. So you're likely to run potentially a range of workloads. Some of those are higher priorities than others. And so what levers does Kubernetes give you to sort of affect the prioritization? And there's sort of two main categories. So these are things that are out there in Kubernetes, but I don't think get as much attention in the average cloud cluster. But they're there. So the first is prioritization. This allows you to sort of rank the priority class of different workloads. These are applied as sort of across namespaces as a category that you can assign to certain pods. They are the primary input to the logic of preemption in the scheduler. So it is what the scheduler will consider when trying to place a workload. If it is a high priority workload, it will look across nodes and try to find nodes with lower priority currently running workloads to actually preempt and kick out, which is separate than eviction, because eviction is when the node itself becomes constrained and the Kubernetes control plane simply needs to recognize that this node is being overtaxed and something needs to be removed, period. So all of these, I think, Kubernetes has never been accused of being super simple. And that's why a lot of these I think, in an edge environment need more careful examination of how they apply. The second of these is called quality of service. Quality of service isn't something you actually apply explicitly in any pod spec or any YAML. It's an inferred, implicit quality of service level. These come from the way you actually ask for resources in a given pod. So there's these three levels: guaranteed, burstable, and best effort. Guaranteed happens when you explicitly declare that every container in a pod has both a memory request and a limit, and a CPU request and limit. So when you exactly sort of pin those resource requests, that's called a guaranteed quality of service. The second one is burstable. This is when the pod is not going to meet this guaranteed criteria, but at least one of the containers in the pod has a memory or CPU request. So this is sort of when you're asking for some portion of the pod to have certain requirements be met. And then best effort is when really no containers in the pod can have any sort of memory or CPU limits, right? So this is where it will sort of fit in between the cracks. And what's interesting is that the prioritization tools and the quality service implicit label are actually orthogonal to each other. So when the scheduler is looking to preempt pods by looking across nodes to see where there are some lower priority pods, it does not consider quality of service. So this is, I think, to me, sort of deep Kubernetes level. If you're really trying to figure out, you're in an edge environment and you're saying, say we're in a retail location and you're running some point of sale services, those you want to be very high priority, high quality of service, and you may have some sort of inventory updating workload that if it has to be preempted and moved to later in the day or when the time is quieter, you certainly don't want that workload kind of causing churn on your high priority workloads. The second one is traffic shaping, which has a couple different facets to it. The point I want to highlight in where it's relevant to edge use cases is that in many remote or edge locations, you're dealing with this bandwidth constraint, and often that bandwidth may be asymmetric. So this is a typical sort of small office, small business sort of commercial cable network sort of profile where you have much less upload than you have download. And you may have, again, multiple workloads that are all sharing that pipe. And so you're more likely to need to prescribe to different workloads that they only have access to so much of that bandwidth on an edge environment, whereas if you're running workloads in the cloud, you generally have fat enough pipes not to worry about metering out bandwidth for different workloads. So there's two parts of this. One is policies and one is related to bandwidth. So policy really deals with permissions. Policy deals with what traffic is allowed. This is also important in the edge. If you want to restrict certain data types from ever egressing from the cluster, you would want to use network policy. Again, it's applied via a network plugin in Kubernetes. It's based on the network external APIs, meaning you wouldn't use, since pods can move around, you're not going to use sort of pod level IPs. You'd always reference the cluster external APIs. And for anyone who's dealt with sort of firewall rules, it looks kind of similar. So I have a snippet here. So the idea is that you have both ingress and egress as types of policy. And for each of those, you can control source and destination, where source and destination might come from something like a label match criteria. So if you want to restrict certain pods can only send data to other pods over the network, or it might be based on CIDR and address ranges for IP level traffic. So the network policy addresses the who can talk to what. The other is bandwidth. So bandwidth is where you're going to limit just how many bytes a given workload can take advantage of on the pipe. And I've put this sort of stack together to show that the way bandwidth management is affected kind of happens at multiple levels. So first, the lowest level is sort of the Linux kernel that's dealing with IP traffic at the kernel level. There's then a Linux tool called traffic control, which is able to set limits to certain Linux network namespaces. So this is where you have a slightly higher order sort of grammar for being able to apply network limits at the Linux network namespace level. You then have the container networking interface. So the way that Kubernetes knows it has network interfaces available to it. So whether that's sort of different NICs in a machine on a node, et cetera, the way Kubernetes has access to that network interface is through the CNI, and there's a bandwidth plugin. And then that plugin can affect bandwidth limits per interface, or if you simply enable the network bandwidth plugin, essentially the control plane will apply pod annotations via that network plugin to specific pods. So I have a little bit to show you what this looks like. So if you simply enable it on a interface, you can say enable true. This will allow the pod annotations to work, which I'll show in the next slide. But you can also specifically limit your overall bandwidth to a specific network interface at the CNI level as well. And so this might be applied if you have multiple network interfaces. Let's say one of them is a modem applying sort of point-to-point networking over a very slow satellite or cellular link, but you have something else where you have across your cluster Ethernet connected to services, and you may not need to limit that network bandwidth on that network interface. If you are having sort of competing workloads and you want to prioritize or allow restrict certain workloads from bandwidth, I think sometimes this is most relevant from a protect yourself against yourself use case, right? So I think many things that go wrong in clouds and computing is when you accidentally sort of DOS yourself, or you accidentally have a bug that results in some sort of runaway network process. And it wasn't malicious, and there wasn't attack here. It's just there was a bug that you got yourself in trouble. And so having something applied to the pod might say, look, we should expect this workload never to need more than a certain amount of bandwidth. If we apply this annotation and we have the container networking plugin enabled, then we know that this will essentially act as a cap, right? One thing that is essentially missing from this Kubernetes space is the ability to prescribe a cluster-wide limit. So all of these still are applying per node. So you still need to sort of do the bookkeeping math of saying, well, I have this interface and this interface and this interface on these nodes, and then I might have these workloads. You still need to somewhere else kind of keep a tally going and saying, oh, well, if I only have a 5 meg up connection, does it add up to 100 basically, or not? And I think that could be one area that potentially would be an improvement for managing Kubernetes on the edge, as something that would span the whole cluster. So I use that as an example of our category 3, which is where does Kubernetes not quite meet all the needs. And I'm going to invite Cindy up to talk about a few more cases here where edge environments might need something that go beyond what Kubernetes offers alone. Here you go, Cindy.
Thank you. So to recap what we talked so far, you heard about why we're doing edge computing, what are the potential user scenarios, and whether Kubernetes can be used already. If not, what are the challenges we are facing? So what I'm going to talk to you later next is about what about beyond Kubernetes? Are we already mission accomplished or not? If not, what's the distance? I think for Kubernetes, it's a cluster resource management and application orchestration tool. Okay, it's an infrastructure and framework. But from an edge computing perspective, I'm listing a few challenges or issues here. think about in the data center, you probably have tens of thousands of servers in a dedicated data center, a single location, or maybe across zones. Okay, but at the edge, IoT computing scenarios, we are talking about hundreds of thousands of machines. Or even if we think of the devices, it can be millions or billions of devices. And those devices and nodes are geographically located in all kinds of locations. Okay, in that perspective, for system engineer, there's no way for them to scale and go to different places to patch, to update. Think about the maintenance cost. From a developer perspective, no way you would worry about if I write an intelligent, very cool application for the edge. You wrote it in your lab or in your office, but you would worry about if I deploy it to the locations, would it work or not? So based on that, I think a container definitely is a very good solution because it's portable, you write it, and then you can deploy it. And then Kubernetes is a good framework as well because from a cloud infrastructure, you can just batch deploy your applications. As long as your node is registered to the cluster, you can deploy it, right? Then we are also talk about for the edge scenarios, the network may not be reliable because the network, due to the geographical location, the network can be connected or disconnected. And the bandwidth is limited as well because, as I said, the scale is big, but your data center is limited. So in that sense, we would think about, in case network disconnected, can the edge node continue work or not? As you all know, for Kubernetes, there's a pod or node eviction concept. So kubelet keeps on reporting the heartbeat to the master node every 10 seconds. In case the controller thinks it's not healthy, then your pod will be evicted or even the node. The concept here is, let's say the goal here is, we want the edge node can be autonomously manage itself. Or even like say, because of what Dan mentioned earlier, due to the latency or the cost benefit perspective, we want things to run itself at the edge. And then it can be autonomous. The other difference for edge computing versus cloud is the hardware, heterogeneous hardware, right? So it can be 108 meg, one core CPU Raspberry Pi to multi-core, multi-gig memory servers. We are talking about such large landscape. And then for the resource-constrained devices, can you run Docker container, Docker engine, and kubelet on it? Think about Docker engine itself at runtime, it can take 100 meg already. If for me, I have a Raspberry Pi, it's only 128 meg. It's already used up. I can't do anything. Okay. Then lastly but not least, the device talking to edge or talking to the cloud, there's so many protocols. It can be HTTP, AMQP. It can also be Bluetooth, Zigbee, or MQTT. There's so many protocols. All those are things we need to consider for edge computing. So here, I'd like to introduce you an open source project called KubeEdge. We recently announced. This project was introduced by Huawei. A few of us in Seattle, we started this effort, and then Huawei open sourced recently. This project, the main idea is we plan to address three main problems. First of all, is the network reliability. as I mentioned earlier, the network between edge node and cloud is unreliable, and the bandwidth is limited. The second problem we try to address is we want the edge node to be autonomous. Okay, in case of things happen, the intelligence can continue work. The third one is we want to build a basic fundamental infrastructure, and on top of that, people can start to build more. Okay, just to share you some status. For the open source, KubeEdge has two parts. One is in the cloud, the other is in the edge. On the edge side, we've already open sourced. On the cloud side, because we have to separate from the production code, it takes a while, but it's gonna be open sourced very soon. So in this slide, you're gonna see the functionalities of KubeEdge and the fundamental architecture. Let me first address the functionality. The KubeEdge will support multi-tenant, large scale of distributed node, edge node, registered in your cloud infrastructure, and you can manage those edge nodes remotely through the cloud infrastructure. Secondly, the agent in the KubeEdge at the edge side is a lightweight agent. At this point, it's about 10 to 20 megabyte footprint. So obviously, you can run on the 120 or 256 meg resource-constrained devices or edge node. And if you use it on your server, obviously, you can save your management overhead. For the network infrastructure, we support multiplex connection. And then for the connection, basically, we use WebSocket to build the connection between the edge node and the cloud. After that, the connection health and heartbeat, we keep on tracking. We also kind of rewritten the TCP stack in part of the software SDN, so that we can identify the node and then they can connect together. The other thing I want to call out is we have a store on the cloud as well as on the edge. The store on the edge and the cloud side, they are synced together. That's a way for us to address the autonomy problem. In case when the network is disconnected, because I have all the metadata synced down from the cloud to the edge already, so all the business logic can continue work on the edge. If we drill deep on the architecture, as you can see on the graph, when you run KubeEdge, it's like you are running a cluster at the cloud. All the data model and the semantics are the same. Basically, you run kubectl, and then you get your node. You can query their status. You can deploy your applications. It's transparent. You don't even know the node is at the edge. And then the main component on the cloud side are two. One is called edge controller. The other one is the metadata store. The reason we have edge controller is like this. In the etcd, for example, after scheduler schedule a pod to a node, basically in the pod tree, you have all the assigned node information. But etcd doesn't support secondary indexing. So in order for the node to get all the assigned pod, so it has to watch the whole pod tree. So you think about what I called out earlier, the network bandwidth is limited. We really want the edge node to sync down only the needed data. So that's why we created the edge controller. So the edge controller will watch the etcd for the kube master, and then it will rewrite the data just just get the data for that node and restructure it and store it in the metadata store at the cloud. Then we get back to the network part. Network part, we introduced a component called KubeBus. If you want to know more details, one of my colleagues had a talk in KubeCon Shanghai this year. He explained in detail about KubeBus. So KubeBus has two components. One deployed on the server. The other component is deployed on your edge node. Between the KubeBus and the server component and edge component, as I mentioned earlier, through WebSocket, once the connection is connected, we rewrite the layer 2 and layer 3 traffic. We monitor the health, and so that it can be connected. Further, I'm not sure how many of you know, Golang has a library which can help you to call the native network APIs to create your tunnel, to do the in-cap, decap. So we also have a proxy which can build the VPN tunnel, those kind of thing, okay? And then the other part I want to say is the agent. Kubernetes is kind of heavy, and then a lot of features are not needed in the edge scenarios. That's why we rewrite some of the functionalities and wrote our own app agent, and it's very lightweight. The other last thing is on the edge side, there's a store as well. So this is the functionality and the architecture. So here, if you go to the KubeEdge GitHub, this is the current status. You can see a lot of people started already. And then I call this architecture, you can see it on the website. You can see the device tuning. We also support the MQTT for the devices already. The one thing I really want to call out as a working group here, this doesn't mean to be the perfect. That's why we have this community and work group. I really hope you gave us feedback or even contribute, because personally, I think this is a great architecture, can help you solve a lot of issues. And then next is the roadmap. You can find the information at the GitHub as well. Just from a long-term perspective, I want to call out a couple of things. One is we plan to integrate with Istio and build a mesh kind of networking infrastructure. And then the other thing is we want to integrate the edge node with the cloud server as well, so that in your cluster, you can have a server machine in your data center and the nodes at the edge. Okay, so I think that's what I have. Here is information about our work group and how you can contribute. We meet every other Friday. We have recordings. If you are interested, you can all go there and catch up. Okay.
And I think we already went a little over, so we'll step out in the hallway for the question part of this. Also, there was a recording intro session here just yesterday, but you should be able to get that, if not now, eventually, because the decks are already uploaded.